Good afternoon, everyone, and welcome to day 2 of SciFest 2025. Very excited today to be once again joined by Grant from the Australian Age of Dinosaurs. And our topic today is, did dinosaurs do maths? So I'm fascinated to hear more about what is going to be happening today. From Grant, who'll be joining us in just a moment. And I'd like to also say a big thank you. Hello, Grant. A big thank you from the Inspiring Australia New South Wales, who has supported our events today and ensured that we can deliver all of these amazing sessions for free. So I'm going to spotlight Grant and I will be in the background helping out. So if Grant asks you a question, you can pop that in the chat. But if you've got a question for Grant, we're going to put those in the Q&A and we will be asking those as we go through. Mostly we'll be covering them at the end of the session. So Grant, thank you so much for joining us, and let's find out, did dinosaurs do maths?
Good afternoon. And yeah, thanks, Karen. So this Science Week, I hope everybody is having a very enjoyable Science Week. I know I am. We started with some activities here at our museum on Saturday and Sunday in town as well. So it's a really big Science Week for us this year, which is fantastic. It's good to see so many people getting involved. So for schools this year, the theme is around decoding the universe. And to me, I'm a bit of a mathematician and physics person, a physicist. So I like to think in terms of some of these mathematical areas, which is, yeah, what prompted me to ask the question, did dinosaurs do maths? Is it even possible for them to do that? Because mathematics is one of those universal things that really does, surprisingly, seem to work everywhere we try to apply it. Mathematics is an amazing tool. So that's what we're going to look at first. What really is mathematics? So, as I said, mathematics is a tool. And that's, if you think of a regular tool, you might think of a hammer or a screwdriver. And of course, hammers are used for hitting in nails, or if you need a screwdriver, you get the flat type or the star type, the Phillips type screwdriver. They come in all different sizes, and there's particular tools that will fit a particular screw head and so on. You need the right tool to do the right job that you have in front of you. And so it's really all about solving problems. How do you fix this board to that board to make a strong roof frame for your house and so on? It's solving problems. So let's have a look at our first problem. And that is, for us, how fast could dinosaurs run? Is it something that we can work out? And the solution, it turns out, is a little bit of mathematics. So that's where we're going to start. Now, before we get there onto dinosaurs, we need to establish a couple of things that are familiar for us. So we need to know, what even is speed? What does it mean to go at some speed, or how fast is somebody running compared to somebody else? So we can define here in a formula, or an equation if you like, how fast you're going. We call that speed. And if you know the amount of distance, how many meters you can cover or travel across in a certain amount of time, we take that distance, divide it by how quickly you can cover that distance, and you've been able to work out your speed. So let's put it to an example that we might be familiar with. If you think about Olympic sprinters here, we've got Usain Bolt there, the fastest sprinter in the entire world so far. Now, on average, he can cover 100 meters in literally only 10 seconds. In fact, he can actually do it in less, but probably on any day, he could do it in 10 seconds almost exactly. So to do that nice, simple piece of mathematics, can we work out a 100-meter sprint for humans? How far is it? Yeah, that's too easy. We can measure 100 meters. We know that distance. The time? Yes, we can work out how quickly it takes one of these Olympic runners to cover 100 meters. Typically, if you're going to be a world record holder competing up there at the top level, you've got to be able to do it in 10 seconds. So let's say, just for a nice simple numbers, that Usain Bolt one day can do his 100 meters in exactly 10 seconds. So to work out the speed, we're going to find this number here. It will be equal to that distance, how many meters he's running, exactly 100 on that 100-meter track, divided by 10 seconds that it took to cover that distance. And if we go, how many times does 10 go into 100? We'll find that the answer is 10. So the speed is 10, but we have to put something on the end called a unit. And these units are very important because the distance was measured in meters and the time was measured in seconds. So a 100-meter Olympic sprinter can cover 10 meters every second. And that way you cover 10 of those, 10 lots of 10 meters makes that 100 meters. And you've covered 100 meters in just 10 seconds. So that's a familiar example that we might be able to think about. It's certainly faster than I know I could ever run, but we can at least relate to that example. Now, if you're thinking in terms of kilometers per hour, it's a much more familiar unit for us to say kilometers per hour rather than meters per second. There's a really simple way of turning meters per second into kilometers per hour, and that is to multiply it by 3.6. Now, I've done that for us already. That turns out, on average, over that 100 meters, Usain Bolt is covering or doing 36 kilometers per hour. In other words, if he were able to keep up that top speed for one whole hour, then he could cover 36 kilometers. Now, that's certainly very unlikely because people who do marathons, 42 kilometers long, certainly take around just under the 2-hour mark. So nobody can run that fast for one whole hour. But for 100 meters, you can certainly maintain a really high top speed. And that sprint speed, that burst of speed, that's something that we're going to come back to for dinosaurs later on. All right. So let's think about dinosaurs. Well, what are dinosaurs doing? They are covering some amount of distance, again, in some amount of time. So the same formula is going to apply. Speed will be calculated by finding how far they've covered and how long it took. Distance divided by time. Okay, so let's check. Can we actually do this? So if we look at their distance, yes, we can find out the distances that some dinosaurs have covered because we have some of their trackways or prints. And I'll show you a picture of that very shortly. But what about the time? We don't have any measure of video footage of seeing these dinosaurs run. So we don't know how long it took them to run across or walk across this particular area where they left their prints. We don't have that yet. So something's missing from our equation. We don't have that time, and therefore we can't work out their speed. So let's look. What can we do to find a solution to this problem? Well, if we look for some other relationships, so things that might give us clues about how animals run and move, whether they're modern animals alive today, and we can take some video measurements and actually work out the sorts of distances and times that they're covering, or we can look at their footprints. So say, for example, their weight. We can estimate how heavy an animal was, its size or height, and perhaps therefore we can make some estimates that might lead us towards the speed and give us some clues about how fast they may have been able to travel. All right, so let's have a quick look here. Just behind me here, we can see something called the Dinosaur Stampede National Monument. Now, this is an area 110 kilometers away from us here at the jump up or just outside Winton. But down here at this stampede, it is literally around 3,500 different dinosaur prints. They estimate it was probably around 300 to 400 different little animals have left these prints behind. But there was one large predator. And you can see these prints over here. They're highlighted by these lights. We'll have a look at a more detailed image very shortly. So those are very large prints, and they've got larger gaps or step sizes between those prints. But every one of these other little marks you can see behind me here is another print from a different dinosaur. Now, these are over 95 million years old, and they've been preserved literally sitting in this site, and were only discovered in the late 1960s when they actually unearthed these. So that's about 70 years ago. Now, let's have a closer look at what these prints look like. So here we've got a nice, you call this a scientific drawing, by the way, because instead of taking out all of the critical information, it's just removed what we don't need so that we can understand and interpret it more easily. So all these tiny little marks, they are the very small prints of these little, some of them, ornithopods or coelurosaurs, or very small, like if you think of a chicken or chook-sized theropod, that's what we're talking about here. But these large prints, 1, 2, 3, 4, 5 of them we can see in that image there, they're from a much larger theropod, possibly or quite probably a predator. And this larger animal has come down to what was the edge of a lake or a billabong, perhaps to get a drink, find some food. And all these other little theropods here, they've scattered out of the way of this larger animal. So they've literally stampeded or run to get out of the way, thinking, I don't want to become that person's breakfast or lunch. So if we look at these, what we're going to start to estimate is the stride length, how far it is from one footprint to the next and to the next and so on. And we can get an average distance between these footprints. And that can give us some very useful information. Then the other thing we can look at is something called the foot size or the length of that footprint, because it turns out that can give us some information about the hip height. How tall was the animal at its hip right here? Because it also turns out that the longer the legs an animal has, in general, the slightly faster that it can actually run or reach a higher speed. And so these are the sorts of relationships that some mathematicians and scientists started to investigate. And they started with modern animals. Because again, obviously we don't have dinosaurs, so we can't step back there and look at how they move. But if we can look at similar modern animals and how they might run or move, then perhaps we can work out some of these factors that can let us work out their speed. So I want you to think of a couple of modern animals alive today that may well be able to be used to do some calculations. Now, in this case, we're thinking about, I wanted to just think about two-legged animals. Two-legged animals alive today, running on two legs that you might be able to compare to a dinosaur, like one of these two-legged theropods. So if you can put a quick answer into the chat there and let us know.
We've got some coming into the Q&A, birds like emus and
Yes,
emus,
excellent.
chicken,
Yep,
cassowary.
exactly. They're the sorts of birds that we start to think about because, as we know, birds are very closely related, or in fact descended from some of those dinosaurs. So they do have, or some of them have, a similar hip structure in their hips and the way that their legs, their femur and lower legs work, and their ankles. So we can actually study modern birds like emus to learn a little bit, perhaps, about some of the ways that dinosaurs may have walked or run, which is very handy. So I'll just point out over here on this side, you can see a little bit of an example how the actual organisms, these dinosaurs, may have looked as they were walking across this site. And if you could zoom right into this image and count every one of those little black dots, that's one of those around 3,500 footprints that make up this trackway out there at the dinosaur stampede. Okay, let's have a closer look. So right here we've got Banjo, our Australovenator wintonensis. So this is Australia's largest, so far discovered, theropod or meat-eating dinosaur. And at the hip, so that's the height from the ground up to the hip point right here, is 1.5 meters. So it's a little bit less than me. It's probably about just below my shoulder height, 1.5 meters. The stride length, as it's called, which is the distance between the back of one print to the back of the next print, is in this case around 3.3 meters. So we can easily take those measurements. The prints, they're literally right there in the rock. They've been sitting there for 95 million years, ever since that mud fossilized. The hip height, it does take a little bit of estimation. One way that they do that is to take the length of the foot from the toe, and you can measure that straight off the prints here, from the toe to the heel or the back of the foot, and they measure that distance. If you now multiply that number by 4, you get the approximate length of your leg from the ground up to your hip. And it's certainly worth, you should try that later on this afternoon when you get a chance. Make sure you take your shoes or boots off. You want to measure the length from your big toe to the back of your heel. Measure that distance, multiply it by 4, and you should find it comes up to the side of approximately the side of your hip. And that works for a lot of animals. It really is surprising. So that's one of the ways we get an estimate here of that hip height of about 1.5 meters. Now that we've got those numbers, we're going to put these into a formula. But I'm going to show you this formula. Don't freak out, because we can make this a lot simpler. And this is the original formula that a zoologist published back in the 1970s over in the UK and London. So I'll point out some of the numbers just so you have a little bit of understanding, but don't stress, you certainly don't need to understand exactly how this works. So this little number here, it's called G, or little g. That is the measure of gravity here on Earth. So gravity is how quickly, when you take an object and you drop it, how quickly it accelerates down towards the Earth. And in our case, for most of us, we use G as 10 because it's approximately 10 meters per second squared. In other words, when something falls, every second its speed increases by 10 meters per second. However, if you're a physicist like me, you might actually use a more precise version. I'm sure some of you will have used 9.8 or 9.81 for that number. But again, it's very close to 10. So we can just put 10 in there. This symbol here, SL, that stands for the stride length. What was that distance between the back of one foot and the back of the next footprint? So that's our 3.3 meter number that we've got there. And H here in their equation, they're using that as the hip height, the distance from the ground up to the animal's hip. Now, if we do a couple of simplifications, we can make this formula seem a lot more simple, which is much nicer to use. So we can find the speed is equal to the stride length divided by the hip height, and then we multiply that number by 1.4 and we subtract 0.27. So that's as simple as that formula can become. But let's put these numbers in. So right here we put in our stride length of 3.3 meters. We divide that by 1.5, which is that hip height up to the hip. We multiply it by 1.4, and then we take off the end of all of that 0.27, and we get an answer. We get this one right here, 2.8 meters per second. So this is the speed that Banjo or that Australovenator was walking, or a strong, fast walk across this trackway, 2.8 meters per second. To turn that into a more familiar unit, we multiply that by 3.6. It's approximately 10 kilometers per hour. So that's not terribly fast. And I guess for reference, if you think about what's your average walking speed, if you're just walking to school, walking across the oval or something, most people walk around about 5 kilometers per hour at an average sort of pace. So this dinosaur here was walking twice that fast. So that's quite a brisk walk, 10 kilometers per hour. It certainly wasn't running or sprinting in that case. So keep that number in mind, 10 kilometers per hour. What we're going to do now is have a really quick look at what might a dinosaur like Banjo actually look like if it were running. And this is a couple of other considerations. So I'll just play this first of all, and we can see the animation. We've got the legs moving. You can see how the ground would be passing quite quickly underneath this dinosaur here if it's running. And this is representing probably the top speed of what we expect Banjo to do. All right. So Banjo there, he's covering, they expect, a maximum speed around about 25 kilometers per hour. Now that is estimated from, again, going that 3.3 meter stride length, the 1.5 meter hip height, and they've been able to estimate that it's doing 10 kilometers per hour in that one example they know of. If you take a few other factors, they call them biomechanics. So that's thinking about the size of the muscle. What sort of muscles do you have? How big are they? How strong are they? The length of the bones, the leverage that a muscle has over a bone in your leg to make it be able to run across the ground. When you put all of those factors into considering how animals move, that's where they get that number around 25 kilometers per hour. But again, we're going to come back to that number shortly because there's a different way to estimate speeds of animals. So at the moment, what do we know? We know for certain that Banjo was walking or briskly walking in these prints at about 10 kilometers per hour. We know from some estimates about the muscle structure and the bone structure, biomechanics, that Banjo could probably run or sprint at about 25 or so kilometers per hour, twice as fast as he was walking in that example. All right. I'm just going to quickly introduce you to another way that we can think about dinosaurs and calculating their speed. So you can certainly later on go and have a look up for this person here, Tom Rocks Maths. He does some really cool maths videos. And this one, he was talking about a very recent study from just last year, in fact, 2024, around the speeds of dinosaurs. And I'm certain you might have heard recently that remember T-Rex in the Jurassic Park movies, and he was chasing those the people in the Jeeps when they're trying to run along in the bush and drive and outdrive the speed of this dinosaur. They have actually reduced what they think the top speed of Tyrannosaurus Rex was based on some of these calculations, which is absolutely amazing stuff. So I'll just take you briefly through a little bit of this to try and give you an idea of how we can use some of this mathematics to still make some amazing predictions. So what they did, they looked at modern animals. So you can see here we've got an elephant, something like a large dog, perhaps a coyote, a wolf. Down here, tiny little mouse. Across the horizontal axis here, we're looking at increasing mass from a very, very light little mouse all the way up to a very large, heavy, couple of ton elephant. So the animals are getting heavier and heavier as we come across this direction. On the vertical axis is how fast they've actually been measured to run. So they can find, put a little mouse in a raceway or a dog and an elephant and track them on video over some distances. And they can actually measure the speeds of these animals. Now, it turns out as animals get heavier and heavier, their muscles get more and more powerful and they can go faster and faster and faster. But somewhere there's a limit. You get to something the size of an elephant and you don't keep increasing your speed anymore. Otherwise, the elephant would be up here somewhere. its speed starts to decrease. There's a particular ratio between the size and mass of all your muscles and how fast you can run. It reaches a peak, a maximum here. Now, for modern animals, it turns out when they put all of these animals on here, this graph, again, it reaches a peak here. I'm sure some of you can guess straight away what that animal right there is. It's got 4 legs, a long tail, it lives in an African savanna, and of course, that would be the cheetah. It is the animal that can reach the highest speed out of all the land animals. But you'll notice it's got 4 legs. Of course, elephants have 4 legs as well, but some of these only have 2 legs. In fact, there's some insects here with 6 legs. So they've taken all of these different animals. So birds, in the case that they're walking on 2 legs, arthropods, insects, mammals, 4 legs, and reptiles. They've taken all of these different modern animals, been able to measure them, their speed that is, based on video recordings. Because we have so many recordings, I'm sure you've seen them in the documentaries where all these predators are chasing some bison or whatever animals across a field. We can actually measure their speeds really surprisingly accurately. And we find that the cheetah, of course, turns out to be the fastest. But now that we've got what we call a model, we can plot something like this. Okay, to explain this word here, extant, that just means that it is an animal that's alive today. So we're using animals, these are all the ones from that previous graph, like the cheetah is that one dot point right at the top here, just up there, the highest, fastest animal right there. So these are all the modern living animals. The extinct ones, that is the opposite of extant, of course, are these dinosaurs that you can see some data points for, the little green triangles just here, and a couple more over there. Now you might be wondering what this line is. There's an almost perfectly straight line going through the middle of all these data points. Up here, curves across the top and starts to fall again. That line is what they call a mathematical model. It's the way you get all of these different scattered data points. If you average them to make the best possible fit, then this is the line that you get. And that's our mathematical model. And they have an equation for this one. It really is quite complex, so I'm not going to show you that one. It really does look a bit scary. But with that, all they need to do is estimate the mass of an animal this time. Remember, this horizontal axis here was the mass or the weight of all of those modern living animals. So if they can estimate a certain dinosaur might weigh 100 kilograms, 200, 300, all the way up to, say, 20 plus tons for one of these large herbivores, sauropods there, then they can estimate, using that model, how fast each of these animals may have been able to run. And that looks really cool because right here, we've got a velociraptor. It's not quite the fastest organism there. Over here, we've got a T-Rex. It's actually coming down in speed. Notice that speed's a little bit lower than the one for the velociraptor. And they had to decrease. So they now believe instead of maybe it was around, they're talking in miles per hour, but instead of around maybe 50 kilometers per hour, a T-Rex top speed maybe is only down around 30 to 40 kilometers per hour. They lowered that top speed a little bit, which was really interesting. And then, of course, something like Triceratops here and a couple of these sauropods, larger, heavier animals, they don't need to run very fast to get away from anybody simply because they're so big. They don't need to run from a predator. A predator almost can't hurt them too much. So that is a really special graph because if we could find where, say, our dinosaurs like Banjo would fit on this graph, we can estimate another way of finding the speed of our dinosaurs. And we'll get to that one in a little second. So, for example, using the dinosaur speed based on the body mass, actually it's a little bit lower than I said there. It's only around for T-Rex 25 kilometers per hour, which is really not that fast. And if you remember rightly, remember way back at the start, an Olympic sprinter for Usain Bolt? That's about 36 kilometers per hour. So maybe for a very, very short time period, an Olympic sprinter could have just outrun a T-Rex, but not for very long. The brachiosaur there, the sauropod, a lot lower, 12 kilometers per hour. The velociraptors, around 55 kilometers per hour. That's a surprisingly high speed. And if we go down here and we put in the mass of Banjo, our Australovenator, it actually predicts a top speed around 60 kilometers per hour, which really is probably a little bit high because compared to the biomechanical model at 25 kilometers per hour, that's what puts in some of the more realistic variances that only you can understand by looking at the muscles and where they attach in the bones. And that's what tells you something about how quickly it actually could have moved its legs. So that 60 kilometer per hour top speed, I think is certainly a little bit unrealistic. But maybe it was a little bit higher than 25. Maybe we could have got to 30 or 35 kilometers per hour. So perhaps we need to go back and look at new calculations, make some new estimates of how fast some of our dinosaurs like Banjo could have been able to run. And that's what science does. We're always going back, finding new models, new ways of reviewing these things. And as we learn more and more, we understand more. And some of our models have to change, our predictions. We get new numbers that are a little bit lower than what we first thought. Or maybe we get some numbers that are a bit too high for what we thought. And we have to change what we understand and how we work with those numbers. All right. So it's time to get to, I guess, the ultimate question that we really want to ask is, did dinosaurs really do maths? Can they actually do mathematics? Well, remember we said mathematics was a tool, and tools, of course, are used to solve problems. So this is where I want you to put some of your answers into the chat for us. The question is, what is the simplest mathematics that you can do, or anybody? What is the absolute, if you think of the simplest mathematics that you ever heard of when you first started school, or maybe even in prep, what was the simplest mathematics that you ever began with? Put some of your answers in the chat. I'm sure you'll get that one pretty quickly.
We've got counting and adding, 1 plus 1.
Yes. Yep. Excellent. And I think you're right there. Counting is probably the simplest mathematics that anybody can ever do. It's the first thing that mum or dad will teach you, the hold up 1, 2, 3. You start to count by recognizing groups of different numbers of objects. So really simple counting is a surprising way of doing mathematics. And we all do it every single day. Now, if counting really does count as mathematics, then could dinosaurs do maths? Well, we would have to be able to know whether or not dinosaurs could actually count. Now, to do that, obviously we can't do a test because we don't have dinosaurs with us anymore. But if we think of the relationship between a predator and its prey, And I'm sure you've all seen the documentaries where we have, you know, something like a lion and it's chasing some gazelle or whatever it happens to be. We can think of those sorts of scenarios. If you're a predator, you might start to think, is it safe for me to attack and grab this meal and take it home? Well, the answer is really, you've just got to check the numbers. If I'm looking at a herd of gazelle and I want to eat one of those, is there one that I can grab and the others are going to leave me alone? Otherwise, I'd be outnumbered because if I go in to attack and then some of them turn around and start to use their horns or their feet and start kicking and throwing and hitting you, you're going to get hurt and you may not even survive. So to be able to be a predator and make that decision, I think, at least, you've got to be able to do some basic counting. So let's have a look just here. Here, of course, we can see just behind me there, there's a little calf of some of these buffalo over in Africa somewhere, and they're obviously trying to go about their daily business. But right here, you'll see a lion. We've got some adult buffalo around here. And notice they're all facing towards where this lion was. So essentially what's happened is the lion was after this smaller, perhaps easier target, just on the edge of the herd, going for the young one there. And mum or dad, one of the adults, has turned around, seen the lion. They've all started to face the direction of the threat, that predator that was there. And the lion has made probably a very, very wise choice. It's recognized that it's outnumbered. It's going to get hit or bucked by some of these horns if it gets too close, could certainly be injured and die. So it's decided it's time to retreat. And that is something called the fight or flight response. And it really does appear that most animals have that self-preservation of being able to recognize if they're threatened by some situation, then they can do two things. They can either stand the ground and try and fight back and hope they survive, or they can take the safe option, run away, live to fight another day, and catch a meal somewhere else instead. So if dinosaurs had the same ability to be able to take this fight or flight method on board, make a rough assessment if they were looking towards, you know, a larger theropod, looking towards a large herd and going, oh, that one on the edge looks like a tasty meal. I might see if I can go and grab that one. But then some of the adults turn around and threaten it by being able to charge, literally just in their numbers. Then I think that that predator might well have been able to count, because I'm sure whether or not it consciously went, oh, 1, 2, 3, 4, no, I'm not going to take 4 on. I'm sure it was literally just a case of being able to make a judgment of group size. And it's going, that's too many. I'm not going to take that risk. So I think certainly that dinosaurs could count. And that means dinosaurs could do maths. So let's have a really quick look here, because dinosaurs, they can still teach us a couple of things about mathematics. Number one, mathematics really is what we'd call universal. It seems to apply in so many different places. It even applies to dinosaurs 100 or 200 million years ago. Mathematics still works when we come to looking at the stride length, the height of the hip of an animal, and so on. We can do speed, distance, and time. It really is quite universal. Fight or flight responses, in some form, they do require a basic counting. And so they're assessing or making an assessment of number, which I'm sure your maths teachers might call something to do with number sense. And that really is what mathematics is all about, being able to take on board some number sense or size, basic counting, and work out the difference of safe, yes or no. Now, finally, I'd like to point out one last thing here. Never be afraid of mathematics because it can't eat you. Dinosaurs, if they were alive, well, that's another story. But mathematics can never eat you, so it simply can't hurt you. And I know a lot of a lot of students in classrooms, especially once it comes to maths, it really is kind of a bit nerve-wracking. You start to get a bit scared of it, but don't ever be scared of mathematics because mathematics is that one tool that you can use to unlock all these different problems. And once you're unlocking all these problems, you'll find that you can get to all of these different answers. And that really is incredible stuff. So let's just put up my final answer here. Absolutely. I think dinosaurs could certainly do basic mathematics.
Excellent. Oh, Grant, thank you so much for that. There was a lot of science and a lot of maths, and because, it is National Science Week and we do look at STEM, which is science, technology, engineering, and maths. So it's really important to think about how maths is involved in all of those things. You can't do science, you can't build things in engineering, and you can't design things in technology if you don't have that maths. So maths sits under all of those things. And
Yep.
we do have some great questions to finish up with as well that have come through
Awesome.
into the Q&A. Carolyn's asking, what would happen if dinosaurs never existed?
Oh, that's a very good question. If dinosaurs had never existed, it's very possible that the process of evolution might mean that maybe even we never existed. So early hominids and humans, which became us, may not have had that pathway to end up as it has turned out today. So maybe there'd be different life forms alive today, not humans, not dinosaurs, but something completely different that certainly would not be us.
And no birds.
Yes, yeah, most likely no birds, absolutely.
Wow. How tall was the tallest dinosaur?
Oh, that's a very good question. I don't think I know the answer to that. Perhaps the Quetzalcoatlus, that really large pterosaur. You're thinking of something, when it's in its standing or sitting position, essentially, was like as tall as a modern giraffe. So we're talking about 4 meters plus in height, maybe 5 meters or more in height. And similar with sauropods, large sauropods, with these long necks and long tails, those sauropods you typically measure their height at the hip or the shoulder. So where they're standing, obviously with those long necks, when they stretch up high into a tree to get some food, they're reaching many more meters. So perhaps if they can get their front legs part way up a trunk, and then they can reach their long neck up even higher, maybe they could reach like 10 meters, perhaps up into the top of the tree.
Yeah,
But their real height, yeah, is most likely a little bit lower, around that 5 or 6 meter mark.
fabulous. What's the slowest dinosaur? I guess the ones that are
Oh.
sitting down.
Yes, or if we go by that graph based off the body mass, it would be the lightest, smallest dinosaur that there was. Because as you get smaller and smaller, your muscles, your body proportions only allow you to run to a limited top speed. So I don't know what the smallest dinosaur was, but if it was, say, the size of you imagine a small mouse or a rat, you're getting down to that sort of size, it's probably only a couple of kilometers per hour is probably all it could run at.
Great. And I guess the heaviest dinosaurs would have been the really big sauropods, wouldn't they?
Yes, yeah, sauropods, titanosaurs, those ones weighing like somewhere over 15, 20 plus tons. That's like 20,000 kilograms. And you see on that graph, once they were really large, they start coming back down in their speed again. So definitely those sauropods, the brachiosaur, for instance, yes, they start to slow down to that. What was that? About 12 to 15 or thereabouts kilometers per hour.
Excellent. Well, this one links to speed. So I think at the moment in modern animals, it's the cheetah that average speed is sort of 80 to 130 kilometers, depending on distance, of course. So we've got here, how is what's the fastest speed and the fastest dinosaur? So using those calculations, what do we think would have been the fastest dinosaur that we know about so far?
Or it's something very closely related to the Velociraptor. Let me just quickly see if I can jump back to that graph and see if we can spot something here on this one. So we don't actually have a specific dinosaur here, but this one right about there, that little green triangle there, just under there, that one is that's the Velociraptor. So that one is around that, I think it was 55 or thereabouts kilometers per hour. So it's
Wow.
certainly in that range, and maybe there's somewhere a slightly faster dinosaur that certainly could have been around the 60 kilometers per hour. That's
Yeah.
incredibly fast. You think of traveling down the road, in mum or dad's car, 60 kilometers per hour. That's incredibly
Well,
fast.
think about it, the school zones that we, have,
Yeah.
40 kilometers an hour. Our average speed in most of our places is 60. So, when you're driving home, have a little think about how that feels. And if you looked out the window and there was a velociraptor next to you, so obviously is that sort of shape and size that you can get to that, to those speeds. We've got another really great question here about what if there was no ice age? I know well, dinosaurs have had lots of different temperatures, but if we think about the more modern times, what if there was been no ice age?
Yeah, that's interesting because one of the things in terms of if you think about biomechanics of animals, of course, mammals, us, we're warm-blooded, so we have to produce our own energy to keep ourselves warm. Dinosaurs being reptilian, most likely were cold-blooded, and so when you get cooler temperatures, of course, we see all the reptiles, snakes and lizards head out, sit in the sun to warm themselves up. And that then allows literally the chemical reactions that allow them to make their muscles work can start to operate or go fast enough so that you really can walk or run once you're warm enough. But if you're too cold, because yeah, the environment around you is so cold that it literally prevents some reptiles from running. They're very slow and sluggish moving, which actually makes them an easy target for something that might want to feed on them that is warm-blooded. So yeah, if there was no ice age, I think it would have changed perhaps the ratio and types of organisms that are most successful at the top of the food chain today.
Great question. Ooh. So here we go. What is the oldest dinosaur? So I guess it's not necessarily, it could be which dinosaurs lived the longest, but also what one of the earliest dinosaurs are.
Well, I don't know the exact one because we're going right back to the Triassic is the earliest start of basically the age of dinosaurs, the Mesozoic. So we're talking around 220 plus million years ago, where the first early dinosaurs really did begin to appear. Uh, in Australia, we've got one dinosaur from the very early Jurassic, which is down near Roma in southwestern Queensland. And that one's around 180 to 190 million years old. It's certainly the earliest dinosaur. And that's a sauropod, by the way, one of these, yeah, large, long necks and long tails. So 190 thereabouts million years old, found here in Australia. But there's definitely some older ones overseas that I really don't know about.
Thank you. We had someone in the chat say that a brachiosaur is three giraffes. If it gives you time. Oh, and
Three
we've got,
giraffes.
yeah,
Wow.
smallest dinosaur. So I think, when we think of small and big, it is all that big variety. You had some species that were small and some species that were big, and everything in between. Okay. I've got a few here I can answer in the chat. Oh, we've got the Euroraptor from the Jurassic period. Thank you. Oh, we've got someone up there in Roma in Queensland, where, of course, there's
Oh,
lots of
awesome.
dinosaurs being found. We've got one of the biggest dinosaurs. I can't even say this one, Millie. Oculoventasis. Um, and someone was asking about whether like other reptiles, whether any dinosaurs used venom. I know certainly in some of the movies they say
Oh.
that they do. But did any dinosaurs have any venom, like some modern reptiles?
It certainly seems most likely, yes. But I'm certainly not aware of any. The the difficult thing about that is finding the chemical evidence for it. So the fossil preservation process, as bones and soft tissue get preserved, it usually is only the bones, the really hard substances that get preserved the best. Soft tissue preservation that is typically where you would find like the venom sacs, like in a snake's mouth or jaw somewhere, those places that store those chemicals, those little cavities. All we would find today are the cavities that possibly may have been evidence for some kind of some kind of venom that they could release, in biting into an animal. But it's really too difficult to find any of the original chemical elements that were there or may have been part of, that poison or venom that they could potentially have had.
Excellent. So, the last couple we've got here. So, someone is asking, what type of dinosaur is Banjo? So, it's an
Ah,
Australovenator, but like what category do we put the Banjo in?
yeah, so banjo fits into a larger category called the theropods, and in fact also fits into something a larger group called I think it's a larger group, the megaraptors. So mega, it sounds like, yeah, that must be a really large raptor, but megaraptors does include Tyrannosaurus Rex. So it is in that same group of meat-eating, yeah, carnivorous two-legged dinosaurs as T-Rex, but they're certainly distant cousins within that group. Because, yeah, in the southern hemisphere where we had Pangaea break up into Gondwana and Laurasia move up to the north, we certainly have never found any close relatives of T-Rex down here in Australia at least, and even much of South America. So there's really not they're separated certainly by time and distance.
Excellent. We are going to finish off with two final questions. One is from Uli about how did dinosaurs communicate?
Oh, I reckon there's a spectacular mathematical answer to that question. Because one of the things that dinosaurs do, and we can see some evidence for that in their skull material, is the type of cavities they would have in their mouth, uh, throat area, and certainly through their nose, that their nasal cavity, and that is how anything makes noise, is blowing air through a cavity, and it's like a horn. You get this really strong, loud noise, and so those cavity shapes and the muscles that push air through it are what make the sounds that a dinosaur could make. So certainly, when you look at the sizes of those, I reckon some people who were into mathematics and music could put together some really good analysis that would tell us some of the types of sounds that dinosaurs might have been able to make.
Awesome, thank you. And we've had a couple of the same question. What's your favorite dinosaur? I know it's a
Oh.
hard one.
Yeah, it always is. And look, if I had to say my favorite dinosaur right now based on speed, I would actually go for Banjo or our Australovenator because I think our earlier estimate of around that 25 to 30 kilometers per hour top speed, I think when we do a bit more research in the coming years, we might find that speed could go up a bit based on this other comparison. I don't think it's going to be 60 kilometers per hour. I think that's a bit too high. But I think that would be really cool because that may well make Banjo one of the fastest, perhaps, dinosaurs in the world, and that would be amazing.
I think that is excellent. I also really love banjo, and we're going to, as I said, share that some information with you about the Australian Age of Dinosaurs, and they've got lots of education resources because there's so many really cool Australian dinosaurs for you to discover. So thank you so much for all of your amazing questions and for joining us here today. And we'll share the recording with you soon. You may want to be creative with some of those equations and see if you can make some of those calculations work as well. Continue on with
Yes.
your science journey. So, thank you very much, Grant, for joining us today and really making our Earth Science Day of SciFest absolutely fabulous. There are so many more sessions to join with us for the rest of the week. So, please check out the SciFest web link and see if there's any other sessions that might interest you. So thank you all very much, everyone, and we will see you
Thanks, Karen.
again soon. Thanks, Grant. Bye.
Thank you. Bye. Happy Science Week.
Oh, yes, absolutely.